Hi, I'm Rowan. Welcome to my talk on threat modeling, securing Kubernetes infrastructure and deployment. I'm the head of security at ControlPlane, and we're a consultancy specializing in cloud-native security out of London. I'm also a contributor to the GKE CIS benchmark and CNCF Financial User Group Kubernetes attack trees. I need to start by acknowledging that a lot of the thought behind codified controls, automated testing and compliance, and the role of attack trees presented here are those of John Meadows, who founded the CNCF Financial Services User Group. We were supposed to present together today, but unfortunately couldn't, owing to circumstances beyond our control. In this session today, we're going to introduce threat modeling and threat modeling Kubernetes. We're going to show how your threat model helps define your control sets. Subsequently, we'll look at how tests associated with your threat model and controls assist with SOC integration and addressing compliance culture shock. And we'll finish with some gotchas and a TLDR. So to start with a baseline, I'm going to very quickly describe the threat modeling process with the 5 W's and a how. In fact, if this is all you take away from the talk and act on with your own Kubernetes implementations, that's a good thing. So what is threat modeling? It seems to be used interchangeably as a noun and a verb. Well, the definition of threat modeling we'll use takes the form of the verb, and it's not just about defining the risks to the system, but about how they are addressed. So why should we do any threat modeling at all? Well, threat modeling can prevent you from finding out about security issues when it's too late. If done properly, establishing a threat modeling program provides the opportunity for the right kind of cloud and Kubernetes migration, where your developers drive from a capability and experience perspective, and security compliance developers work in tandem to enable that in a secure, compliant fashion using the threat model. Effectively, this means shifting security left in the development process and identifying the security requirements for the developer. So you should really start threat modeling as early as possible. As soon as a shared understanding of an architecture starts to develop, you should be threat modeling. This provides real benefits. If you find a security issue early and are able to change the architecture to be more secure before anything has been implemented, you'll have saved a huge amount of rework and likely arrived at a more secure and usable implementation. If security issues are picked up later in the process, you'll be trying to retrofit security into the architecture. You may be successful, but the chances are you'll end up with a more complex and compromised solution. So threat modeling just doesn't stop with the first release. Once you've got an in-flight project with an existing threat model, when the tickets and features are defined for each release, evaluate and update the threat model around those specific features and tickets. So who should contribute to your threat model? Basically, everybody. Each stakeholder has something to contribute and their own unique view of the world. Now, architects have a vision for the system. If that system is already in use, then DevOps will know how that works in practice, and they'll know about those little tricks and deviations they have to get things working that may stray away from the intended architecture. Your security operations center, your pen test teams, your threat intelligence teams are also useful people to have on board. These people know about the tactics, techniques, and processes that attackers use. Bringing these teams to the threat modeling sessions is critical. After all, these are the teams who are skilled at breaking into your systems. Who better to validate your assumptions on what is secure? Another point to note here is that if you are threat modeling an existing system, a powerful technique could be to take the threats you've identified, ask one of the pen testing team to attempt to exploit those threats. It's a great validation of your threat model if you start identifying threats with the real world evidence produced by the pen testing teams. Last but not least, include product owners, business analysts, and internal users in your threat modeling sessions. These people know as much as there is to know about their data, and they can help determine the boundary between necessary business function and security. Now, a few words of caution here. If you start workshopping with all of these stakeholders, that only works best if they're completely familiar with the project and the solution. I've been in a few sessions where that hasn't been the case, and frankly, it's been chaos. So if you need to, arrange some preparatory sessions to establish a baseline amongst all these individuals first. Always make sure that you have some documentation or architecture diagrams available that detail how the system works to refer to during these sessions. Also, if you're threat modeling early on with that team, this set of stakeholders, and you've yet to define the architecture, then just prepare to draw a lot of mock-up architecture diagrams. Sadly, threat modeling is really done best in a room with a whiteboard. Unfortunately, as we all know, it's just not possible right now. Additionally, if you're at a large organization, it's actually likely that your stakeholders will be globally distributed anyway. So video conferencing it is. And with that, you'll be at the mercy of the collaborative tooling that you're allowed to use by your organization. So be wary of that when you're planning your sessions. Finally, how does one actually perform a threat model? Well, here's the basic threat modeling process as defined by Adam Shostak and adopted by OWASP. There are 4 simple steps. What are you building? What can go wrong once it's built? What should you do about those things that can go wrong? And did you do a decent job of analysis? So for the first thing, what are you building? Steps all about information gathering and context setting, understanding the nature of the data, criticality of the system, what the architecture is and how it's provisioned and maintained. The second step is obviously the point at which vulnerabilities in the system and resulting threats are identified and crucially prioritized. Following which you're going to create a backlog of mitigating security requirements, new architectures, bug fixes, and so forth in order to answer what should you do about those things that could go wrong. The final step is to identify whether you did a decent job of your threat model. So you're going to review the outputs from the previous 3 steps. You're also going to incorporate external sources, such as pen testing at this point. Once a threat model has been established for a system, it's this step that's repeated, just to make sure the answers to the first 3 questions are relevant to the system at the current point in time. It's all been quite abstract so far. But what does this threat modeling process look like for Kubernetes? Well, the 4 C's of cloud native security are cloud, clusters, containers, and code. So to secure your full stack, you're going to obviously need to consider the configuration of the cloud service provider, the cluster, what the containers comprise of and how they're configured to run, and the security of application code itself. Now we can broadly address the security of the latter 3 through the design of the cluster and the CI/CD pipeline. And regardless of whether you're a small or large organization, it's good practice to provide standardized components for application teams to consume. So you'll provide a cluster for them to use, or a means to provision and scale their own clusters. You'll define the baseline configuration of that cluster, and you'll place some restrictions on what applications can do in terms of configuring that cluster. You'll also obviously provide those application teams with a CI/CD pipeline used to build container images and deploy those to your Kubernetes cluster. So for each of these patterns, you're going to end up creating reusable threat models. And those threat models are generally going to be along the lines of cluster provisioning and scaling, cluster runtime and cluster configuration, and then threat models for the application CI/CD pipeline. And the outputs of those threat models will define the architecture of the standardized components and patterns your application teams will use. This all raises a really important point. Doing a runtime threat model is not enough. You need to ensure you think of the architectural solution from an end-to-end perspective. You need to ensure that you're truly thinking through things through, right from the client experience, through deployment, to how operations staff utilize your cluster solution. You can have the most secure system in the world at runtime, but if it's exploited because you forgot about supply chain security and deploying the system insecurely, then you've wasted your time. So you really have to think this through from an end-to-end perspective. So defining what you're building, any good architectural diagram will do. You can also use open source tools like Cloud Mapper to get as much info as possible on your environment. But just to mention data flow diagrams here, data flow diagrams are really important, really useful for breaking down what you're building into flows, processes, trust boundaries, and stores within a system. And once you have that depiction, that makes a technique called stride, which I'll describe in a couple of slides. It makes it a lot easier to do. So if your architectural diagrams aren't fit for purpose, consider drawing a data flow diagram instead. You can draw data flow diagrams of a specific interaction, like a Kubernetes pod launch, or the whole system, like this depiction of a simple CI/CD. Again, you may need to create multiple diagrams just to reflect the end-to-end solution. So now you have these architectural diagrams and you have all of this information. You need to start identifying what can go wrong. Now, if you're experienced in the threat modeling and security space, then brainstorm to your heart's content. Annotate your architecture diagrams. Make copious notes as you let your imagination run wild. If you've not threat modeled before, it'll be helpful to use a framework. Stride and PASTA are two examples. So STRIDE's an acronym, stands for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. One can use STRIDE to characterize and identify the kinds of threats that affect processes, data flows, and stores within your system. And STRIDE is most commonly applied or used in conjunction with data flow diagrams because, as I said earlier, data flow diagrams are diagrams that do explicitly display those processes, data flows, stores within your system. There are other more explicit sources of threats. For example, the MITRE attack matrix, and also reverse engineering benchmarks can also form a valuable source. One warning, a thing to bear in mind, is that you need to define when to stop identifying threats. If you're not careful, you can threat model in an endless spiral of despair, picking out every issue out there. So when do you stop? If you're experienced in this space, and everybody's familiar with Kubernetes and cloud native solutions, you can time box your activities because you'll know roughly when you're done. Otherwise, if you're threat modeling for the first time, if you have one really good stride attack per element represented in a data flow diagram, that's an okay first pass. Finally, when you're identifying threats, there are a wealth of great talks and existing threat models available within the community. And so it's no surprise that I'm going to talk briefly about CNCF Financial User Group attack trees. So in conjunction with other members of the CNCF Financial User Group, we threat modeled the whole Kubernetes system by asking what can go wrong. We looked at attacks of the API server, Secretd, kubelets, exploiting aspects of CNI or CSI. We looked at compromised workloads and the various permissive configurations that could be accidentally granted. We also looked at some cloud provider integration and metadata API file attacks. And these attack trees are open sourced in GitHub for your use. Now, attack trees are a highly useful threat modeling tool, and you should use them whilst identifying your threats. They provide a formal, methodical way of describing the security of systems based on varying attacks. Basically, you represent attacks against the system in a tree structure, with the goal as the root node and different ways of achieving that goal as leaf nodes. Attack trees were coined by Bruce Schneier in 1999, and we've got a brief or simple example of an attack tree to the right here. It's simplified for the point of explanation. Attack trees can be quite large and sprawly, difficult to present on PowerPoint slides, so we've got this abridged version here. So to start drawing an attack tree, you start with a negative outcome that you want to avoid. So in this case, it's at the top, and it's malicious code in the workload. You subsequently ask how it could be achieved to flesh out the rest of the tree. To explain the key on the right, the shape of each node dictates whether the node is an AND or an OR. AND nodes require both conditions joining the node from below to be true, whilst OR nodes indicate that what lies beneath are multiple ways in which the node can be realized. So one way to have malicious code running as part of a Kubernetes workload is to deploy a poison container image. And if you look below that node, in order to deploy that poison container image, you need to poison the image within the container registry, and the image needs to be deployed. And in this case, it will be deployed as part of a normal release. Going further down the tree, in order to poison the image in the container registry, you will obviously need to obtain the image pull secret, and you're reliant on that pull secret having write and overwrite privileges within the container registry. Finally, there are actually 3 different ways in which you could obtain the image pull secret. You could make a Kubernetes API request, or you could use a running container with host file system access, that's accessing the password on the host, or we can obtain it from a kubelet using the unauthenticated port, for example. Now, attack trees are useful tools for collaboration between dev teams and security. Security teams who aren't necessarily au fait with all the cloud-native technologies often recognize the high-level outcomes that must be avoided, such as information disclosure, data exfiltration, and so on. When security teams are faced with new technologies, they don't know exactly how they're achieved, but attack trees are a great way of fleshing this out with technical detail below, and helps establish a common point of reference between development teams and security when discussing the overall security posture of the system. Now, if you don't want to use attack trees, as I said, create tables or annotate your own diagrams. Here's a threat model of a cluster at runtime. It's not pretty, but it's perfectly valid. Just labeled all the things that could go wrong in an architecture diagram. Don't get too precious about your diagrams and architectures. You will be redrawing them and updating them countless times as you build your threat model. So initially, don't worry about your connections being a little bit off, because you'll be redrawing those lines soon enough. Now you've got a whole host of threats identified. Well, what are you going to do about that? Well, to define your control sets, evaluate and prioritize your threats, then map controls directly onto them. You could end up with a particularly busy architecture diagram like so, or you could annotate your attack trees by breaking different branches with an appropriate control. We'll talk a little bit more about attack trees later. So when you look at selecting controls, what controls do you have to choose from? Well, frankly, there's loads. Here's a quick menu of controls. Just like any good menu, don't order everything, it will make you sick. We'll talk about how you minimize the number of controls you need to implement later. So in the networking space, if you're concerned about the compromise of a container and subsequent pivot across the network, there's Kubernetes network policy for starters. If you're running a service mesh, then there's the ability to have ingress and egress rules and access controls between workloads at layer 7. Additionally, you've got infra firewalls, whatever they may be called for your cloud provider, be it security groups or NACLs, or simply just firewall rules. These will provide you with networking restrictions at the node and subnet layer level at layer 3 and 4. Also, some container native IDS and IPS systems can now be configured to restrict the network connections made by running containers. Well worth considering. What controls can you use to constrain a compromised container at runtime, maybe one that would attempt to break out onto the host? The first thing is just to get the basics right. Define a secure security context for your pods and containers. It's all the usual stuff. Run as non-root, don't allow privilege escalation, drop all your Linux capabilities, and use AppArmor, profiles, or SE Linux if you can. Container compatible IDS and IPS systems are pretty prevalent too, so use them, ones like Falco. There are also paid solutions that offer a lot more capability than just runtime protection, with container image scanning, admission control, et al. So if your org likes to throw money at things, then these are well worth using. Just finally, over the last few years, sandbox and isolation technologies have started to emerge. Now, implementations differ, but the goal is the same. It's to isolate the running workload from the host's kernel as much as possible. The 3 that are currently the most prevalent are Kata, gvisor, and Firecracker. It's a space to watch with interest. There are currently a few limitations to investigate before you dive into using these for everything. For example, service mesh compatibility. So, whether accidentally or maliciously, your users are going to misconfigure your clusters, workloads, or just accidentally break things. Again, getting RBAC right is one of the basics. It's not easy though, but thankfully there are plenty of open source tools to help on that front. Make sure you enable the Kubernetes admission controllers The CIS benchmarks have recommendations on that front on what you should enable. And finally, no talk on Kubernetes RBAC or policy is complete these days without mentioning the Open Policy Agent, provides the ability to enforce custom policy, and appears to be the future in the pod security policy space. There are a couple of implementations you could use as admission controllers. It's a Kubernetes native implementation in the form of Gatekeeper. You can still use plain OPA to enforce your other custom policy if you so wish. Now, the majority of the controls that I've just mentioned are to protect your cluster from a compromised container. It goes without saying that the most important element in preventing this is embedding security within CI/CD, which is a toolkit itself. There's a wealth of information on security checks and tooling at each stage of the container build pipeline. But just a note of increasing importance and focus, particularly within financial services, is the ability to attest that a container image you have built has been subject to all of the security tests implemented as part of your pipeline. This involves collecting metadata from each stage of your pipeline and validating it at cluster admission time. Graphius paired with Kritis and Entoto are the open source technologies to consider in this space. So you might read all of that. You might have a threat model with loads of threats in it. And then you might pull together all of your controls, decide to enforce defense in depth, and end up with this, an example cluster from an infra perspective. You can see how the infrastructure controls segregate nodes, allowing one to enforce controls on networking at the infrastructure level, and theoretically segregating the cloud permissions a workload can access at the instance level. That's theoretical, we'll touch on that later. The architecture gets even more complicated when you look at all the services and configuration that will need to be configured within Kubernetes itself. My advice is not to do all of this, particularly straight off the bat, unless you have a really, really good reason to, and your threat model will justify it. Instead, start simple. Of these complementing control sets, there's absolutely no need to implement an entire category of controls to demonstrate defense in depth. Your security architecture needs to be as simple as possible to mitigate the threats you've identified to an acceptable level. Bear in mind, the more complex your security architecture becomes, the more automation you need to provision to both provision and automatically test clusters. In effect, this is the ability to provision a cluster, supporting services, and run a full suite of tests from just one push of a button. It's the only way to ensure that a complex solution is maintainable and scalable. So when choosing the minimum set of controls, risk has to be the determining factor. Prioritize the threats in your threat model according to the risk they pose. That will help you go from a lengthy list of threats to understanding where to start first, which threats are significant enough to eliminate, and the starting set of controls required. At this point, I'll again extol the virtue of attack trees. As controls are devised, labeling and plotting them onto your attack trees as a means of breaking the branches are a great way of showing you how your security controls can theoretically combine to stop attacks. They'll also demonstrate another means of defense in depth, not by doubling up on controls for a certain category, but showing how seemingly unrelated controls can mitigate attackers from working their way through your system. Now, automated testing is often overlooked when implementing controls or codifying controls. Just like in mainstream software engineering, you wouldn't dream of releasing code without testing. So too with codifying security. You must write tests to validate the efficiency of the control or the efficacy of the control. If the first time your control is tested by the attacker is at runtime, you're in for a bad day. So the only way to validate control implementation is to do so repeatedly using automated tests. In some cases, you may be able to focus on implementing the controls in such a way that you can automatically test them at runtime in addition to the SDLC. This gives a continuous security monitoring capability. It's like the holy grail of automated security. It's important to note, you test the threat to be mitigated, not the specific implementation you've coded for your control. In other words, check to make sure you can't access your S3 bucket via HTTP, rather than validating your code is as you expected while implementing it. This is a common mistake often encountered by junior developers who test their implementation or the happy path, rather than truly checking the intent of their code. Finally, in the test space, one potential project to be aware of is a proposal made to SIG Security to secure Kubernetes end-to-end via configuration and codified controls tests for the Department of Defense. Earlier in this talk, we discussed the importance of ensuring that you threat model from an end-to-end perspective and ensure that the SOC and other operational teams are involved. Well, taking this to its logical conclusion, we must implement controls for our threat models and ensure we implement any appropriate detective controls with our SOC teams. Also ensuring we have suitable automated testing in place. After all, what good is a detective control if it isn't written appropriately to genuinely alert a SOC team member or process? So, step 1, do your threat model. Told you how to, now off you go and do it. Step 2, reproduce the attacks identified repeatedly against test clusters and gather the signals. Step 3, take these signals and work with the SOC to configure their scene tool. You may need some training at this point. You may want to use your attack trees so your SOC has situational awareness in order to understand how the signals they're receiving relates to an attacker's path through your system, and so forth. You'll probably need to review audit configurations during this step, just to make sure logs are neither sort of too full or too slim. Finally, you want to rerun your test cases and make sure the SOC lights up. And you want to keep iterating on this. So as your system develops, you'll identify new threats, you'll identify new detective controls. You'll need to keep going back to the SOC. So if your organization is new to cloud, you're in the middle of a Kubernetes implementation, and you haven't thus far engaged the compliance and InfoSec team, be aware that they are likely to be in a state of absolute shock as they evaluate your architecture for the first time. You're going to need to approach them prepared. Scaring them straight into a no is a real risk here. So come armed with your security documentation and threat model. Show them there's some precedent followed in terms of standards adhered to, like the CIS benchmarks for Kubernetes and related test results from KubeBench. Also of note, if you're in GCP, is that Google have open sourced GKE patterns that demonstrate adherence to PCI DSS. And I believe that's the subject of another talk here at KubeCon. Again, if you're following this pattern or using this pattern, you're demonstrating precedent and adherence to standards. You can also get one step ahead of the curve by mapping controls to your compliance requirements. Thus, your tests prove your compliance, and you move the assessment away from something that is just checklist-based. Realistically, though, not all requirements bestowed upon you by your organization will be testable or even applicable to cloud native. So if policy rewrites are required, then use that as an opportunity to write policy in such a way that compliance can be demonstrated with automated tests. Just going to finish with a couple of gotchas. So I mentioned node segregation earlier on as a tool for implementing security. You can put firewall rules around your different nodes at the infrastructure level. You can also make sure that your nodes have different instance permissions so that your workloads are not able or only able to assume a minimal set of roles, so you could keep privileged roles on different nodes. Well, that's still too much thinking along the happy path. So Tim Orclow and Greg Castle gave an excellent talk at KubeCon San Diego on how using node segregation does not guarantee security within a Kubernetes cluster. Their demo showed attacks that included being able to reschedule malicious workloads on other nodes. These were historically possible and shouldn't be possible now, but the talk is worth revisiting and taking into account when deciding how important node segregation really is within your security architecture. So if you run a service mesh in your cluster, it will need some Linux capabilities that would not be authorized if you had implemented a restrictive pod security policy. So for example, with Istio, if you have an installation that does not use the Istio CNI plugin, which is still in alpha, then Istio init containers will be run in each of the application pods. And each of these require netadmin and netraw Linux capabilities. Now, if I recall from about a year to 18 months ago, the Istio containers back then ran with, I believe, maybe the privilege flag and root. Don't quote me on that, but it appears that things are much better now. Regardless, you will still need to relax your pod security policies to allow these capabilities. Now, the eagle-eyed among you will recall Liz Rice's talk from KubeCon 2019 in North America on the dangers of CapNet Raw. However, the attack from that talk doesn't succeed within Istio service mesh, hence the asterisk. So regardless, if you want to lock this down, the solution is to implement some custom policy using OPA within an allow list for Istio containers specifically. So the largest gotcha of them all is that large regulated organizations with existing on-prem infrastructure tend to take that mindset into the cloud. So be wary and keep in mind that introducing cloud native and Kubernetes into a large regulated organization requires as much of a cultural change as a technological change. As you all know, large regulated organizations like financial services organizations have numerous compliance requirements. That results in security architectures that place special emphasis on a few areas: strict change control, standardization of security architectures, and extensive logging, audit, and protective monitoring requirements. Unfortunately, the byproducts of that focus over many years within an on-prem environment have resulted in the following practices: heavily manual change control processes, which are slow, time, and resource consuming, a reliance on detective rather than preventive controls within security architectures. So an example of that would be the manual change control process that involves admin ClickOps, and then reliance on the SOC to detect any misconfiguration made by that admin after the event. Now, neither of these practices are particularly secure, maintainable, or scalable within cloud, and so are obviously red flags to be wary of as you start your migration to Kubernetes or cloud. So in short, I know we're running a little bit over. Threat model: do it early on, get everyone involved, keep it up to date. Draw attack trees. They're really useful. They break down high-level threat outcomes into discrete steps, providing a great resource for security and for writing tests. They allow you to determine the controls needed to secure your solution without over-egging the cake. They also provide a great source of situational awareness for the SOC. Make sure you apply and test your controls in an automated fashion, remembering to test the threat the control mitigates, not the implementation of the control itself. And once you've done all of this, you'll be able to run these automated tests against test infrastructures so that integrating with the SOC should be relatively easy. So we'll finish with the obligatory hiring slide, and thanks for attending the talk.